This video is made on behalf of the EXEL lab at the University of Nevada, Reno. I'm going to be demonstrating our workflow or pipeline for attacking a real-world bridge problem by converting a model of said bridge into a graph and a form which our genetic algorithm can use to develop an efficient solution for bridge inspection robots. So to start this off, I'd like to demonstrate our model of the real-world bridge we will be attacking. In this case, it's the Golden Gate Bridge, as you can see here. This is a high-quality model, and what we're interested in here now is this truss structure down here. As you can see, it's relatively simple, but as is the case with many bridges, it's very, very large. But what this model allows us to do is closely inspect the truss structure so that we can understand it, and then proceed to the next step, which is to utilize a software tool written in Python, previously written, which is available here on my GitHub, Graph and Bridge Generator, as you can see. And this was previously developed to generate truss-like bridge structures in the form of a graph so that our genetic algorithm can use them. So the missing link here is utilizing this tool so that it produces a truss structure which is of the same topology as you see here in the Golden Gate Bridge, and also produces it to scale so that the distances associated with each of these members is to scale to the real bridge. So I'm going to walk you through that part. There is a good amount of public information about the Golden Gate Bridge. So here you can see some few calculations that went into this work. So publicly available is the fact that the suspension span is this long, 6,450 feet. And by observing the model that I just showed you, you can see that the truss structure has this repeating pattern. It's just the same thing again and again and again. And by my estimation, there are 288 of these patterns per side on the outer truss structure. You'll notice there are two layers here, but on the outer one, there are 288 of this repeating rectangular pattern. You can see it here. I'm talking about this pattern, this rectangle that I'm tracing out with the mouse right now. So that pattern repeats 288 times per side. And the basis of using the way we're going to be generating this truss structure is going to be based around this repeating pattern. So anyway, with some knowledge of the size of the bridge, we can deduce the approximate size of this pattern and all its dimensions, so that when we generate the graph, we know approximately to scale the size of each of these patterns and therefore the size of each of these beams. So that eventually when the genetic algorithm runs and we produce an efficient route, we will know the approximate length of that route in feet in this case. So let's talk a little bit more about the graph generator. As I said, it has previously been written to produce graphs of arbitrary size. And now we want to modify it to produce graphs, or produce a graph in the style of this Golden Gate Bridge. So previously the tool produced bridge-like graphs, truss structures similar to this one. You could modify the size, the number of layers, and so forth. But now we just want to do it exactly like so. So by slightly modifying the Python program, we are able to do just that. I'm going to demonstrate the program generating said truss just now. So notice we have this updated version graph generator Golden Gate Pi. Don't worry about these command line arguments, they're not relevant in this case. It tells you the size of the bridge you've just created, the size of the graph. This doesn't look too clean, but if I zoom in here, it'll let me. Now we can see, it didn't come out so clean, but you can see that the topology is just the same here. It's a bit difficult to see because the scale is messed up, but you'll notice that the pattern is the same. You see this V pattern repeating. And the axes here are quite messed up, but the data that was actually saved is to scale. The distances are correctly to scale. And I can demonstrate that by opening the CSV file that was generated by the same program. So that would be created here. You'll see it was just created 11:27 a.m. Bring that up for you. And this is, you could almost see the structure in the CSV file, which is pretty funny. But as you can see, the distances here, 11 feet, 11 feet, 11 feet, those are the calculated distances for the size of those horizontal and vertical members. And this 15.83, that was the approximate to scale length of those diagonal members. So you could see the length of every member generated was in fact to scale. And this CSV is essentially everything we need for our genetic algorithm. This is exactly the input data file that our genetic algorithm is designed to use. So hopefully I've demonstrated that with just a little bit of tailoring, we can take any model, high-quality model of a real-world bridge, adapt it slightly for our purposes, and quickly have a genetic algorithm run on said bridge and produce high-quality results. Thanks for watching. This has been a video for ExoLab.